Hello everybody, I welcome you all to NCAS Geology class. In today's class, I will discuss about the morphology of crystals. What are the different parts of the crystals and how these parts are being described, what are the notations which are used to indicate the different morphological features of the crystals, that I will discuss. Let me start. Crystals are solid bodies bounded by surfaces which are usually flat, and these faces are arranged on a definite plan pattern which is an expression of the internal arrangement of atoms. They are formed by solidification of minerals from gaseous phase or from liquid phase, and the process is called crystallization. So, from liquid, from gases, the solidification takes place, in which there occurs a proper atomic arrangement, as a result of which a solid body is being produced, and that solid body is being described as a crystal. The morphology of crystals is the study of external shapes and the arrangement of crystal faces. Following are the terms that are used to describe the external morphology of crystals. First, faces. When you look at any crystal, we see that it presents plane surfaces that bound the crystal. This is a type of cubic crystals. So it is bounded by these faces, these plane flat surfaces, these are called faces. So there are 6 faces which bound this cubic crystal. So faces are the plane surfaces that bound a crystal and are called as its faces. The planes that bound a crystal are called as faces. These faces are usually parallel to net planes containing the greatest number of lattice points or ions. So these faces, they reflect the internal atomic arrangement. So they are parallel to net planes containing greatest number of lattice points or ions or atoms. The faces may be made up of like faces as we find here in cube. So this type of cubic crystal which presents like faces are said to have a simple form. So all faces are alike in case of simple forms, and there may be cases in crystals where the faces may be unlike, or different types of faces may be present to bound the crystal. Here the faces are not in same shape, so not like faces, unlike faces. Here we can say the crystal is not in simple form. So the like unlike faces result due to arrangement of ions in the same type or of dissimilar type along net planes. Accordingly, the faces develop, and these faces, they give rise to forms of the crystals. So when you talk about form, it may represent a number of like faces. A crystal made up of entirely of like faces is termed as a simple form, as we see in case of cube, octahedron, dodecahedron. In cube there are 6 faces, in octahedron there are 8 faces, in dodecahedron there are 12 faces. So, this is a cube. Here this is a cube. All faces are alike. So, it is a simple form. Cubic forms are all most of the or almost all the crystals that occur in cubic system are of simple forms. Thus, they are made up of like faces, and they can exist in combination, or they can exist with dissimilar faces, but the most of the forms are made up of like faces. There may be combination of forms in which we find the occurrence of dissimilar faces, but each form is generally represented by like faces, and that's why all the cubic forms are said to be simple forms. If the crystal is made up of two or more simple forms or two or more kinds of faces, it is described as a combination form. So, here it is cube, here it is a square face, here it is a square face, but this is a rectangular face. This is a rectangular face. This is a rectangular face. This is a rectangle. So, there are 4 rectangular faces, 2 square shaped faces. This is a case of a crystal that belongs to tetragonal system. Here in above diagram of a crystal, there are 2 kinds of faces. Horizontal faces are square shaped, and they make one kind of form, that is called basal pinacoid, and all vertical rectangular faces, they together make a form which are called as tetragonal prism. So, crystals present, so this crystal presents a combination form, but each form when you talk about it must be made up of like faces, and there may be combination of forms in a crystal. In that case, we describe the form to be a combination form. And we have another form, that is open form. What is open form? The crystals that are made up of faces which do not enclose space are called as open forms. For example, this is a open form. We have, this is one face, this is one face, this is one face, and this is one face. We have 4 faces. This is solid made up of 4 faces, and bottom is open. This form is called pyramid. So, pyramid is a open form. This form is a pyramid, and if it is of this type, then it is open form. But there may be 4 faces, but it may be closed form, which may enclose space. For example, if this is a type, sorry, in case of tetrahedron, if we draw a tetrahedron, same 4 number of faces, but it will be a closed form because it will enclose space. We cannot get into the crystal as the faces bound the crystal. So, this type of face. So, there are, this is one triangular face, this is one triangular face, this is one triangular face, this is one triangular face. So, 4 faces they bound the crystal, and it is a tetrahedron, but it is closed. But here this is 4 faced, but it is open because these faces they occur in this manner. So bottom is open. So it is a pyramid is open form, whereas tetrahedron is a closed form. So in closed form, the simple forms, these are simple forms that enclose space and are, that's why described as closed forms. As we see here, it is a upper part is a one pyramid, lower part is another pyramid. So it is dipyramid. So dipyramids are closed forms. Tetragonal dipyramid is a closed form. All faces are alike and enclosed space, that's why it is a closed form. Then we will describe what is holohedral form, what is hemihedral form, what is hemimorphic form, what is enantiomorphic form, what is tetrahedral form. So let us discuss what is holohedral form. In each crystal system, there are forms in its normal class, that is class with highest symmetry of the system concerned, and that class possesses the forms which are called as holohedral forms. There, in case of normal class, all forms are said to be the holohedral forms because they show maximum symmetry possible in that crystal system. For example, if you talk about crystal isometric system, the forms such as the forms of hexoctahedral class such as cube, octahedron, dodecahedron, trapezohedron, trisoctahedron, tetrahexahedron, so and hexoctahedron, these are the forms of normal class of isometric system, and these forms are called holohedral forms because they show highest symmetry possible in the system concerned. So these are holohedral forms of cubic system: cube, octahedron, dodecahedron, trapezohedron, trisoctahedron. So these are the holohedral forms of cubic system. Then what is hemihedral? Holo means complete, complete in symmetry, that's why complete in faces. There cannot be crystals having more than the number of such faces. For example, in hexoctahedron, we can never have any crystal of cubic system which can have more than 48 faces, because 48 face represents to hexoctahedron and it is a form of normal class of isometric system. But when you talk about hemihedral forms, hemi means half of the holohedral forms. So it must be a lower class of a system. The lower classes of a crystal system may have forms which represent half number of faces of the corresponding holohedral form. So this form of lower class is described as the hemihedral form of the concerned holohedral form of that crystal system. So for one holohedral form, there are two hemihedral forms described as positive and negative hemihedral forms. For example, octahedron in normal class has 8 faces with symbol 111. It has two hemihedral forms, that is tetrahedrons. It can be described as a positive tetrahedron with, this is the general form, general symbol, and we have the negative tetrahedron which is having the common face like this. So negative tetrahedron. So, these are the faces of negative tetrahedron, these are the faces of positive tetrahedron, and they correspond to the faces of octahedron. If we join together, if we take into account the faces of positive tetrahedron and negative tetrahedron, they together account for all the faces of octahedron. So, the hemihedral forms of octahedron are positive and negative tetrahedrons. That has been shown, positive tetrahedron, negative tetrahedron. Now, let us discuss what is hemimorphic form. This accounts for the form of lower class in a crystal system where the faces only exist at one end of the vertical crystallography axis. Hemi means half, morphic complete morphology. So, if it is a type of crystal, so this is a complete crystal having upper pyramid, lower pyramid, it is dipyramid. If we take into account only these four faces, that means half of the faces are present and lower half faces are not there. So, faces are only concentrated in at one end of the crystal axis and not there at the other end. This type of form is called as hemimorphic form, that has been described here. So, hemimorphic forms account for the occurrence of faces only at one end of the vertical crystallography axis. Such a form is called a hemimorphic form of the corresponding holoidal form, as we find in case of tourmaline. So, hemimorphic forms have no center of symmetry because faces are there at one end, not on the opposite side. So, this side is not there. So, this type of form can never have center of symmetry. That is why hemimorphic forms are devoid of center of symmetry. Now, this is the tourmaline crystal. So, here the faces are there in the upper part, they are not present in the lower half. So, tourmaline is showing hemimorphism. The form shows dissimilar faces about the two ends of an axis of symmetry, and that axis of symmetry is called the polar axis. On the upper end we will have other types of faces. This type of face and the faces on the other end of the vertical axis, they will not be similar. So, dissimilar faces accumulate at the two ends of the polar axis, and this type of form occurring at one end of the polar axis is described as a hemimorphic form. So, half number of faces will be there at one end of the polar axis in case of hemimorphic forms. Then let us discuss what is tetrahedral forms. Here tetrahedral means 1 by 4. 1 by 4 number of faces of the corresponding holoidal form is tetrahedral form. Here the form is made up of 1 by 4 number of faces of the corresponding holoidal form in the crystal system. These forms have neither center nor plane of symmetry. In case of hemimorphic form, there was no center of symmetry, but here in case of tetrahedral form, there is no center, no plane. For example, holoidal form is hexoctahedron. It is having 48 number of faces. Symbol is HKL. But when you talk about hemihedral form, it is hex tetrahedron having 24 number of faces. Symbol is HKL. If it is tetrahedral form, it is tetratoid, 12 face HKL form. So these are the forms of cubic system. This is holoidal form, this is hemihedral form, this is tetratoidal form. So these are lower classes. This is holoidal class or normal class. Mineral is tetrahedrite. In case of mineral tetrahedrite shows tetratohedral form. Then we have the enantiomorphic forms. These forms of crystals show neither plane nor center of symmetry. They represent the holoaxial classes. Here that we have already discussed, holoidal form, hemihedral form, tetrahedral form, they represent the classes which are not containing only axis of symmetry. But when you talk about a form which is enantiomorphic form, it is only representing the classes that show only axis of symmetry. So these are holoaxial classes. Holoaxial classes are called as enantiomorphic forms, such as 2, 2, 2, 4, 2, 2, 6, 2, 2. These are holoaxial classes. So these classes, they show enantiomorphic forms which are related to each other as right-handed forms and left-handed forms, and they do not have any plane or center of symmetry. They have only axis of symmetry. Here the crystal shows two positions, so that one is the mirror image of the other. These two positions are described as right-handed and left-handed forms. So in two positions they will match each other as if they are the mirror images. In that case they are described as right-handed form and left-handed form, and in other positions they will not match. That's why they lack center of symmetry, they lack plane of symmetry. They only possess axis of symmetry. For example, quartz. It has right-handed form and left-handed form, which are described as enantiomorphic forms. What is enantiomorphic? If we take into account two hands, left and right, they are not superimposable. Hence, they form enantiomorphic pair. Same thing occurs in minerals of holoaxial class. They match in one position, forming mirror image of each other, and they are described as right-handed form and left-handed form, as we see in case of quartz. And general form, the form that does not bear any relationship with any symmetry element, that is, it is not parallel or perpendicular to one or more symmetry axes or planes present in the holoidal class of the system, that is described as a general form, the form that does not bear any relationship with the symmetry element. So, all the forms of triclinic system are general forms, and as they do not have plane or axis of symmetry. There are two classes, 1 and 1 bar. This is pinacoidal class, this is pedial class. They do not possess planes of symmetry, do not possess so only they may possess a center of symmetry, as we find in case of pinacoid, no plane, no axis. So, this is the general form. So, all the forms of triclinic system are described as the general forms. And then let us discuss what is unit form. Unit form or fundamental form or parameter form. This is a form whose faces cut the crystal axis at unit distances. So, the face symbol will be 1 1 1 or 1 1 0, 0 1 1, 1 1 0 0. One zero one, like this. Unit distance, the intercepts will be at unit distances. The face will cut the crystal axis at unit distances. There the form is described to be a unit form. Now let us discuss what is the limiting form. Limiting form, these forms have fixed Miller indices. In each crystal system there are 3 limiting forms. In cubic system, cube, octahedron, dodecahedron, their symbols are fixed, 1 0 0, here it is 1 1 1 and here it is 1 1 0. In each system there are 3 forms which have fixed Miller indices. Similarly, in hexagonal system, basal pinacoid, not 1, 1 not, 1 bar not, 1 1 2 bar not. So, these are the fixed symbols. So, similarly in tetragonal system, these are the 3 forms which are fixed. Orthonormal trigonal system, these are the faces, these are the forms which are fixed. And these Miller indices of the forms that are fixed, they are described as limiting forms of the crystal systems. So, this is all about what are the different forms, and let us describe some common forms of the crystals such as pedion, pinacoid, prism, pyramid, dipyramid, diprism, domes, diametral prism, scalenohedrons, sphenoids, trapezohedrons and scalenohedrons, rhombohedrons. So, these are the different forms of names of different forms of the crystals. Pedion, it is a open form represented by one face only. Class 1 in case of triclinic system, all forms of class 1 are pedions. They represent one face only, and symmetrically they are said to be because symmetrically one face is complete. If we talk about the symmetry, then in that case we can say a pedion can have no other symmetry elements. So with respect to symmetry elements, it is complete, and it is a one-faced form, that is pedion. If it is two-faced form and it is an open form, it is not enclosing space, it is made up of two faces only, each of which cuts one crystal of axis and remains parallel to the other two. These are called pinnacles. If these are the three crystal of axis, a face will cut one crystal of axis, this face and this face. These are the two faces, they cut only one crystal of axis at two ends. So they are called as pinnacles. They are parallel faces, and there is no pinnacle in cubic system, that we have to remember. When we talk about prism, these are vertical faces which remain essentially parallel to the vertical axis or C crystallographic axis. So it is a open form because it is open from the top and open from the bottom. It is consisting of 3, 4, 6, 8 or 12 faces, and these are essentially vertical and they cut only the horizontal axis and remain parallel to the vertical axis. If this is a tetragonal crystal, so these four faces, these are vertical faces, they are parallel to C axis. So this is prism. These four faces, they make a form which is called as prism. If we have this type of face between the C axis and the horizontal axis, they are called as pyramid. Pyramid is open form consisting of 3, 4, 6, 8, 12 faces, and which essentially cut vertical axis and cut one or more horizontal axis. And if it is dipyramid, then it becomes closed. This is dipyramid. This is a pyramid. This part is pyramid. This part is pyramid. Together they make dipyramid. So together they enclose space. That's why closed form. Only pyramid is open form. So dipyramid is closed form. Domes. It is open form, intermediate between prism and pyramid, and its face cuts one of the horizontal axis and the vertical axis. It is otherwise called as horizontal prism. It is there in orthorhombic and monoclinic systems, domes. They cut the C axis and one horizontal axis and remain parallel to the other horizontal axis. This face is parallel to this axis, cutting C, cutting B, parallel to A. So this is a dome. So like this, these are the dome faces. This and this, they make a dome. So domes, they are open form because they cannot enclose space. This side is open, this side is open. So it is open form, intermediate between prism and pyramid, and its faces cut one of the horizontal axis and the vertical axis, and it is otherwise called as horizontal prism. It is found in orthorhombic system and in monoclinic system. Diametral prism. It is formed by combination of three pinnacoids which together enclose space. They occur in orthorhombic, monoclinic and triclinic system. There we find three types of pinnacards: A pinnacard, B pinnacard, C pinnacards. They enclose space. These are called as diametral prism. Then let us discuss what is spinard. Spinard is made up of two faces joined with each other and are noted for a axis of two-pole symmetry. Spinard is an open form consisting of two faces, shape wedge-like. Shape is two-faced form having axis of one axis of two-pole symmetry separating these two faces. So this is edge shaped. Two faces joined together in an edge. These faces are not parallel and are usually look like a pair of sloping surfaces meeting along an edge. It is a tetrahedral form, that is just 1/4 of the faces of the full holohedral form. Spinard. It may be of two types: tetragonal spinard four-faced, orthorhombic spinard four-faced. Found in tetragonal system, monoclinic system, orthorhombic system. Dispinard is closed form which is made up of four faces. So spinard, open form made up of two faces. If we take these are the two faces. These are the two faces joined in this edge, and if these are the two faces on the opposite side, then they may enclose space, and this will give rise to a dispinard. This is dispinard. But when you talk about spinard, it is two-faced, having an edge, and they generally show a axis of two-fold symmetry. And if it is a trapezohedron, each face is a trapezium-like or trapezium-shaped faces. It is a closed form made of trapezoid faces or kite-shaped faces. It is arranged symmetrically around an axis of threefold or fourfold, and it always possesses even number of faces. Trapezohedron. We have tetragonal trapezohedral class, we have trigonal trapezohedral class, hexagonal trapezohedral class, we have trapezohedron in case of cubic system representing 24 faces. We see the mineral garnet exists in form of dodecahedron, exists in form of trapezohedron. These are the two common forms. Dodecahedron and trapezohedron are the common forms of the mineral garnet. So trapezohedron is a closed form, and each face is a trapezium. Then scalenohedron, it is a closed form. It is made up of scalene triangular faces. Even in number, related by threefold axis, as we see in case of calcite, that is rhombohedron, and scalenohedron, it is dog tooth spar. Dog tooth spar, like this, face symbol is like this, dog tooth spar. So this is scalenohedron. Each face is a scalene. Each face is a scalene. Each face is a scalene. Scalene triangular faces, and they enclose space. Even number of faces are there. They form closed forms. As we see in the case of trapezoidon, similarly it is the case with scalenohedron. We have then another form is rhombohedron. Rhombus shaped faces, as we find in case of 3 bar, each face is rhombus. In rhombohedron there are 6 faces, 3 on the top, 3 at the bottom, representing a threefold axis of symmetry and possess a center of symmetry with no horizontal plane of symmetry. It has center of symmetry. So rhombohedron. And cubic forms are cube, octahedron, rhomboedocahedron, tetrahedron, trisoctahedron, hexoctahedron, pyrethrohedron, diploid. These are the cubic forms. In total, we can say there are about 47 natural crystal forms, out of which 25 are open and 22 are closed forms. And almost all the forms of cubic system are closed. In isometric, 5 basic closed types. These are cube, octahedron, dodecahedron, tetrahedron, trapezohedron. These are the common 5 basic closed types. There are also more closed types such as hexoctahedron, diploid, but about 5 but diploid, but above 5, these 5 types, cube, octahedron, dodecahedron, tetrahedron and trapezohedron, they are said to be the fundamental forms, and no open form is there in cubic. So in tetragonal, open forms are basal pinacoid, prism for first order, second order, ditetragonal prism. So these are four types open form. Closed forms are dipyramid, a first order, second order, tetragonal, ditetragonal, dipyramid. So these are the 3 closed forms in tetragonal system. 4 open, 3 closed. Similarly in orthorhombic, 4 closed, 3 open. In monoclinic, 3 closed, 4 open. In triclinic, 1 bar is open, 1 is open, but generally it is called as closed because with respect to symmetry it is complete. Pedion is open faced pinacoid, 1 bar is pinacoid, 1 bar is pinacoidal class, 1 bar. Each form is represented by 2 faces which are parallel to each other. In case of pedion, it is 1 faced, form is 1 faced. Single face treated as closed in symmetry sense. It has no axis, no plane, no center, hence closed with respect to symmetry. As it is not enclosing space, we can say it is a open form. But with respect to symmetry, we can say it is closed because it has no plane, no axis, no center, pedion. But 1 bar is a pinacoidal class, it is having a center of symmetry, its form is made up of 2 faces, it is enclosing, it is not enclosing space, it is open form. Pinacoid is open form. In hexagonal system, there are 9 open forms, 10 closed forms. Which has been mentioned here, 9 and 10 closed forms. So we have 47 types of forms occurring in nature, out of which closed are 22 types, open are 25 types. So this is all about the form, all about the faces. Now let us describe what is edge. 2 faces joined together in one line, and that line is called as the edge. When two adjacent faces meet on a line, they produce an edge. Solid angle. When three or more faces meet at one point, they produce a solid angle. Zone. If in many crystals it is found that a group of faces are found to be arranged in such a manner that their intersecting edges are parallel to each other. Such faces whose edges are parallel to one crystallopic axis, they are said to constitute a zone. A line which passes through the center of crystal and lie parallel to this line of intersection of these edges is called as the zone axis, which is represented by a square bracket. Let us say this is the zone axis, which is this is the zone axis, C axis. 0, 0, 1 face perpendicular to the zone axis. The face is vertical. Here, this is the zone axis. This is not the face. Here, face axis are vertical. If a zone axis is 1, 2, 3, it is represented by vectors from origin as given below. First, 1 unit, we go 1 unit, then 2 unit parallel to B axis 2 unit, then 3 parallel to C 3 unit. So, from the origin to this point extended, this gives the direction of 1, 2, 3 axis. This is the zone axis. So, a number of faces whose edges are mutually parallel, they constitute a zone, and the edges, they run parallel to the one of the crystallopic axis, and that axis direction is the zone axis direction, and zone axis is always represented by a square bracket, and it is perpendicular to the face concerned. For example, if it is 1, 1, 1, this is the zone axis, it is perpendicular to 1, 1 face. So, this axis perpendicular to this face, this is the face, this is the axis. So, zone axis is always represented through the, they are considered to originate from the center. By taking the vectors into account, we can draw the zone axis, as we have drawn the 1, 2, 3 axis, zone axis here. So, interfacial angle, it is the angle between the adjacent faces, or the angles subtended between the two perpendiculars to those faces. The faces must be adjacent to each other, and the angle between them, or the angle between the perpendiculars down to them, gives the interfacial angle. It is measured by contact goniometer, and this angle is related to atomic structure, and hence the angle is fixed between two faces, and it is called as the law of constancy of interfacial angles. The law of constancy of interfacial angles states that the interface angles between corresponding faces are constant for all crystals of a mineral. It is called law of Nicola-Steno. This is one face, this is another face. The angle between them, perpendiculars, this is the interfacial angle, or this angle. This angle is the interfacial angle. Interfacial angles between cube and cube, 90 degree. Octahedron and octahedron, 70 degree. Dodecahedron and dodecahedron 60 degree. Cube and octahedron, remember, we have to remember 54 degree. Cube and dodecahedron, it is around 45 degree. Octahedron and dodecahedron, it is 35 degree. That is fixed. These interfacial angles are fixed. Whatever may be the mineral, if it is showing a cubic form, then this must be the interfacial angle. Interfacial, then relation between the faces and edges in crystals. Edge is described as, edge is equal to half of number of face F1 into side S1 plus form F2, face F2 with side S2. So, this is the formula which determine the edges. For example, we have cube of 12 edges. It has face F, S sides of the faces. So, edge is how many edges are there? So, it is half into face 1, side 1. Face, if it is face 1, it has one face, side 4. Second face, side 4. Third face, side 4. Fourth face, side 4. So, like this we have 12 edges. If it is cube, if it is octahedron, half into 8 faces into 3 sides. Each face is having 3 sides. So, 8 into 3, it is 12 edges. We have 1, 2, 3, 4, 5, 6, 7, 8 edges. So, this is the formula which are used to describe the number of, or to find out the number of edges present in a crystal. Relation among edge, face and solid angle is this is the relation. Solid angle is equal to number of edges plus 2 minus number of faces. For example, if it is octahedron, edges are 12 plus 2 minus faces are 8. So, 6. So, there are 6. So, this one, these are the 6 solid angles. 6 solid angles in case of cube. In case of octahedron. In case of cube, there are 8. So, 12 is the edge, number of edges, plus 2 minus 6 is the number of faces. So, it becomes 8. There are 8 solid angles in case of cube. So, this is the formula to determine the number of edges, and this is the formula to determine the number of solid angles. So, in my next class, I will discuss about the zone axis, how zone axis is being found out, and then we will discuss about the elements of symmetry. Let me discuss this zone axis, how zone axis is being calculated in the next class. In my next class, I will discuss on the elements of symmetry. So, let me complete this zone axis. So, in order to calculate the zone axis symbol, we write the two faces in this manner. Two faces, in order to calculate the zone axis. What is zone? The faces whose edges are parallel, they constitute a zone. So, let us consider two faces. The zone axis between these two faces can be found out in following way. Let us say 1, 1, 0, 1, 0, these are the two faces. We have to write the face symbols twice. This 1, 1, 0, again 1, 1, 0. Below it write the second face symbol, 1 naught naught, 1 not 2 times we have to write. Then first digit and last digit of each line, this line are disregarded, and the remaining numbers are joined by sloping arrows as indicated below, and they are multiplied. In each set, the product of 2 is subtracted from the product of the second is subtracted from the product of the first. So 1 into 0 minus 0 into 0, this one. 0 into 1 minus 1 into 0, this one. 1 into 0 minus 1 into 1 here. So this zone axis becomes 0, 0, and minus 1 is written as 1 bar. So in bracket, square bracket, this is the zone axis for the phase 1 1 naught and 1 naught naught. If we make a axis like this, a phase of this type will have symbol 1 1 0, and a phase of this type will have 1 0 0, and both are running to parallel to C axis. So we have got the zone axis here, the C axis, perpendicular to 0 0 1 phase, which is the basal method. Similarly, we can have other phases, and accordingly we have found out if a phase occurs in a zone where phase symbol and zone axis are known, we have to verify it. Let KLM is the phase and UVW is the zone axis. By considering these two, we can say whether this phase is lying in this zone. It will be verified whether KLM phase lies in the zone of UVW. It can be possible if KU plus LV plus MW is 0. But UVW must have to be reduced to its simplified form. Simplified form, we have to represent it in simplified form, otherwise we may not get 0. Check if 1 1 1 lies in this axis. So 1 1 1 1 1 1, they are all multiplied, they are added, it becomes 3, which is not equal to 0. So 1 1 1 phase is not lying in this zone. Check if 3 to 1 is in 0 1 0 3 bar zone. 3 into 1, 2 into 0, 1 into 3 minus 3. So it becomes 0. So 3 to 1 lies in this zone. Problem, check if 1 1 0 lies in 2 minus 4 2. 2 minus 4 2 is to be reduced to, it is to be reduced to 1 minus 2 1, or 1 2 bar 1, and then solve. So 1 into 1, then 1 into minus 2, then 0 into 1. When they are added, it becomes minus 1, which is not equal to, so it is not in this zone. In this manner, we find out the phases which occur in a zone or not by taking into account the zone axis and the phase symbol. In my next class, I will discuss about the elements of crystallography, elements of symmetry in crystals. Thank you all for giving a patient hearing to my